At any given moment, roughly 10,000 commercial aircraft are airborne over the planet. Each one is tracking a corridor through the sky assigned to it by a network of controllers who have never met the pilots, never seen the aircraft, and are managing the whole thing through radio and radar. The system that coordinates all of this is air traffic control, and it is arguably the most complex real-time logistics operation in human history. Air traffic control has one central purpose: keeping aircraft separated from each other. In practice, this means maintaining minimum distances between aircraft at all times, typically 5 nautical miles horizontally or 1,000 feet vertically in controlled airspace. Every time an aircraft enters controlled airspace, it is handed to a controller who is responsible for it until it is passed to the next controller. No aircraft in controlled airspace moves without a clearance. The pilot cannot simply decide to change altitude or route. Every maneuver has to be requested and approved. This is not bureaucracy for its own sake. It exists because at the speeds and altitudes involved, an uncoordinated change by one aircraft can conflict with another aircraft the pilots cannot see, separated by a distance measured in seconds of flight time. ATC is divided into distinct phases that mirror the journey of a flight. Ground control handles everything on the airport surface, the movement of aircraft from gate to runway. Tower control manages the immediate airspace around the airport, including takeoffs, landings, and the zone within a few miles of the field. Approach and departure control takes over as aircraft climb or descend through the airspace surrounding busy airports, typically up to 10 or 15,000 feet. And en route control, handled by area control centers, manages the high-altitude cruising phase, the long stretches of airspace between departure and arrival. Each sector has a controller, and each controller is responsible for a defined piece of sky. At a major international airport, dozens of controllers may be working simultaneously across these different positions, each managing their own small piece of a coordinated whole. Controllers see aircraft on radar displays that show position, altitude, call sign, and speed. Primary radar works by bouncing signals off aircraft and measuring the return. Secondary surveillance radar, which is more commonly used, interrogates a transponder on the aircraft and receives a coded reply that includes the aircraft's identity and altitude. This data feeds into systems that project where each aircraft will be in the next few minutes. The controllers work from this picture, issuing instructions by radio on assigned frequencies. There is no typing, no texting, no email. Every instruction is spoken, read back by the pilot, and confirmed. This read-back procedure exists because a misheard altitude or a wrong runway can be fatal. When a controller clears an aircraft to descend to flight level 350, the pilot reads that back verbatim before touching any controls. The rules governing how far aircraft must be from each other were developed through incident investigation over decades. The 5 nautical mile horizontal standard in en route airspace came from analysis of what distance gives controllers enough time to issue a correction if 2 aircraft are converging. The 1,000-foot vertical standard exists because altimeters have tolerances, and a tighter margin would erode the safety buffer when both aircraft are exactly on their assigned levels. Wake turbulence adds another layer of rules. A heavy aircraft like a Boeing 747 generates powerful vortices behind its wings that can roll a smaller aircraft over. Separation minima between different weight categories exist specifically to let those vortices dissipate before the following aircraft arrives. These are not conservative estimates, they are the product of modeling, testing, and hard lessons learned from accidents. Every flight is a series of handoffs. When a departing aircraft leaves the tower frequency, it is transferred to departure control. When it climbs through departure's sector ceiling, it transfers to the first en route sector. As it crosses into different countries, it transfers to the national ATC authority of that airspace. Each handoff involves a coordination between controllers, the first confirming that the aircraft is on its assigned track and level, the second accepting responsibility for it. This chain of handoffs happens dozens of times on a long international flight, invisibly to the passengers, continuously, around the clock. There are no gaps in coverage. The moment an aircraft crosses from one sector to another controller is already watching it on their screen. The system is not perfect. Wake turbulence, equipment failures, weather, and human error all introduce risk. But the safety record of commercial aviation owes a significant debt to the structure of air traffic control. 10,000 aircraft in the sky at once, none of them deciding for themselves where to go. That level of coordination does not happen by accident. It is the product of decades of engineering, procedure, and the quiet professionalism of controllers working through every hour of every day to keep the sky from becoming a place where aircraft simply find each other.